Good afternoon. I want to thank everyone for joining me today. This is Mike Medoff with Exeter Consulting, and today we're going to be talking about a 61508 compliant development process. So we'll be focusing today on a process that can be used to develop products or systems that are compliant to the 61508 standard. And I won't get into a lot of the background of the standard during this webinar because we only have a limited amount of time. So I'm going to assume that you know a little bit about 61508, the functional safety standard, what it's about, or even if you don't, that you've maybe been told that you need to develop a product to meet this standard, and so we'll just focus on the what you need to do to develop such a product right now. All right. As I said, my name is Mike Medoff, and what I mainly do here with Exeter Consulting is I work with manufacturers of products or systems, with developers who are trying to get those products developed to be compliant with IEC 61508 or similar functional safety standards. And I help them essentially get their products to be compliant and get their processes to be compliant. If you have any questions throughout the meeting, feel free to ask through the Q&A menu. You can just type in the question, and I'll see on my monitor that there are some questions there. And I may answer them as I see them. I may save some of them for the end. It just depends a little bit on how the overall timing of the presentation is going. But feel free to ask them at whatever point that you have them. Okay, so this webinar is targeted at those who must develop hardware and or software compliant with 61508. I'm going to provide an overview of a development process that can be used for such development, and I'm going to define the safety life cycle from the perspective of hardware and software development. I'm not going to get into every aspect of the development process, mainly because of the time constraint. So I may jump around, but mainly I'll try to focus. I'll just try to give an overview of everything that's part of the process, and then focus on the areas that might be more interesting. And this presentation is based on a book by the same name, Functional Safety, a 61508 SIL 3 compliant development process. And so if you are listening to this presentation and you find you want more details on some of the areas, this book is available on our Exeter website at exeter.com. All right, just a quick, just to put in perspective, the goal of functional safety, which is essentially what the 61508 standard is built around. And the goal of functional safety is that the automatic safety function will perform the intended function correctly, or the system will fail in a predictable or safe manner. So the whole concept of functional safety is you identify hazards that you want to protect against, and the hazards might be something like a high concentration of a toxic gas, or it might be a high temperature or pressure condition, due to some process that's occurring, a potential explosion, any number of hazards that could cause harm to someone. And you identify the hazards, and you come up with functions, safety functions, that will mitigate against these hazards. So the safety function might be to detect the concentration of gas, and if that gas concentration gets too high, to sound an alarm, or to ventilate the area, or do something to help keep people safe, and keep people and equipment safe, I should say. And so the key part, one key part in here is this word intended to function correctly. So once you define these safety functions for the systems, the standard essentially helps to develop a system that functions correctly when needed, and if it doesn't, if there's a failure that occurs, it'll fail in a safe manner. So it'll fail in a manner where it automatically alerts people that there's a problem, possibly shuts down the system. But one of the main goals is to minimize hidden failures that nobody knows about for years until suddenly a safety demand comes up. Okay, so there are there's essentially a development life cycle that's defined in 61508 that is a sequential life cycle, and it starts with the hazard analysis that I talked about before, goes on to the identification of the hazard, trying to figure out whether the likelihood of hazards, consequence of hazard, whether they need to be mitigated or not, and whether you need to have some sort of system in place to mitigate against these hazards. And then once you do, the standard goes on to talk about the development life cycle of such products. You know, how do you develop the products so that they're compliant to the safety functions, and so that they're reliable and once again and fail safe. And so there's the sequential process, and then there's also various processes that apply throughout the whole life cycle. And so first I'm going to talk a little bit about those processes that apply through the whole life cycle, and then I'll get into a little bit more of the sequential process, essentially starting with the development of the system or product. All right, so the first general process is the documentation process. And one of the key requirements here is to create templates for standard documents and checklists for document content. So the templates for the documents will essentially provide a standard look and feel to all similar documents, and it also supplies a little bit about what the content of that document needs to be, because essentially you include sections defining what needs to be in the document. And so that helps ensure that everyone includes the right information and that documents are easy to navigate through. And then the checklists essentially are looked at and filled out once the document is completed as part of a review. So all documents will need to be reviewed, and most documents will have checklists essentially for the content. What is the content that needs to be in this document, and is it complete? Does it have all content? So this really applies all throughout the development life cycle. In every case where you have some sort of documentation needed, these three items, the templates, checklist, and review, will apply. And in the book that I had mentioned previously, we do list specific checklists and specific templates for the key documents. All right, and then the last item related to documentation process is to apply configuration management to documents using a document management system. So this is essentially to be able to provide control and management of what documents exist, so they can be easily found, and so it can easily determine which documents apply to a certain release of the product or a certain configuration. And in addition, this also is associated with control of documents. If someone wants to change a requirement for a product midway through development, they shouldn't be allowed to just go through and change the requirement. They need to follow a process where the change is reviewed, the impact is studied, and it's approved. And so the control and change of documents is also controlled by this configuration management process and the document management system. All right, another common area that applies to the entire life cycle is personnel competency. It's fairly obvious that in order to develop a product that's reliable and safe and meets the requirements, you need to have people that are competent and knowledgeable on what they need to do. So this includes knowledge on safety standards and safety processes, like we're talking about here, but it also includes knowledge on whatever a person's given area of work is, such as if you're doing software development, you might need to know, you would need to know about the programming, you need to be knowledgeable in the programming language used, or the design methodologies used, or how to do module testing, etc. So whereas personnel competency is a common thing that most companies certainly consider as part of the normal day-to-day operation, this standard 61508 takes a little bit further and says you really have to analyze for the project and make sure that you have competent people and to document that beforehand. And so one way to do that is to create a matrix similar to the one shown here, which essentially shows in the columns the different roles that will be fulfilled on the project. You have somebody who's a requirements engineer who's responsible for creating the requirements, for example, a system test engineer who's going to test the product, a hardware architect, a software architect, software test engineer, etc. So people fill different roles, and based on the role you fill, there'll be different knowledge that you need to have, essentially, and skills that you need to have to perform those roles. And so that's what the rows are. They essentially show the different skills that you need to have, and then the boxes will show which skills apply to which roles. And so if there's an X in a box, that means that that role is needed. If there's like this X in parentheses, that means it's partially needed. The person needs to be partially knowledgeable in it. They don't have to be fully knowledgeable. And so finally, once you do this and you lay out what the requirements are for competency, then you just need to go through and analyze the people that are assigned to the project and ensure that they have that competency. And it won't be uncommon that you'll find, well, maybe somebody doesn't have a specific skill that's needed, and you'll need to come up with a plan to rectify that. And so that's what the color coding shows here. Green means the person fully has that skill required. Red means they don't, and yellow means that they partially have it. And so in any case where there's yellow or red, you would then have a plan to say this person needs to have some training in a certain area, or this person might need to have a mentor work with them on the project, someone who can kind of train them on the job or review their work as they go along. So it doesn't always have to be formalized training. It's just some way to make sure that they achieve that competency, or somebody's able to review that they're meeting that competency. And as there are certifications for many items out there today, there's different software certifications and testing certifications. There is also a certification associated with functional safety, and it's called the CFSE, Certified Functional Safety Expert Program. And this is something that can be used, certifications like this can be used to demonstrate competency. Now, not everyone on the project would have to have competency in functional safety. Most people would just have to have competency in the area that they're working on in terms of functional safety. But it would certainly be helpful if there's at least a few people on the project that have this level of knowledge. And so, like any certification, this is an exam-based certification. Also has some experience-based. And there's 4 types of exams. So on the application side, there's the process industries and the machine industries. And on the development side, there's a hardware and software specific version of the exam. If you want more information on that, I think it's cfse.org, I think is the website for that. Another process that's very important to safety is change control. And studies have shown that a common cause of failures in products is you might have a product that's been developed very carefully, been rigorously tested. However, when it's time to change the product, the same levels of rigor are not always followed. And so you need to have a change control process in place that ensures you analyze the impact of all the changes. And that's what this shows here. The process would essentially be initiated by a problem report, or an enhancement request would get written. And that would ultimately get into some kind of database, like a change request database that would track all the changes that have been requested. There's then a group that gets together that reviews the change request periodically, known as the Change Control Board. It's usually a cross-functional group, people from development, maybe people from test, people that represent the voice of the customer, such as marketing or product support. And so this group reviews the change requests, decides which ones are worthwhile to consider, and those that are worthwhile considering, then an impact analysis must be done on. And so that impact analysis essentially analyzes what is the impact on functional safety. If this product was developed to be compliant with 61508 and is supposed to be fail-safe and reliable, what is the impact of these changes? What could the changes affect that? So certainly there's some kinds of changes. If you're just painting it a different color or something basic like that, you can the impact analysis is very simple, and you say, no, the safety is not affected at all by this. None of the safety components are changed. But then if you're changing specific software related to the safety function, then obviously that could affect the safety, and you need to make sure that it doesn't. And the way to do that is, and what needs to get identified in the impact analysis is essentially what verification measures will be put in place, what kind of checks and tests and reviews, etc., will be done to make sure that the change does not compromise the functional safety. And then once the impact analysis is done, the change control board essentially makes a decision again. Now they have a better understanding of how much work is required. Do they want to go forward and do it, or do they want to stop work at that point? Assuming they go forward, you need to, what they describe as, decide where in the safety life cycle to re-enter to development. So essentially what this means is when you're making a change, you need to follow the standard development process starting at this re-entry point. So if the change you're making is associated just with software code, for example, and no design, no hardware is changed, that's where you re-enter the life cycle in the software implementation phase. And then you have to do the steps that follow that, such as software testing, integration testing, code reviews, etc. But you don't have to do any of the hardware tests or any requirements reviews because you started later on in the process. So that's essentially the change control process to ensure that changes are made without affecting the functional safety. Verification is another area that applies throughout the life cycle, and essentially what verification is a way to test and evaluate the outputs from a given safety life cycle phase to ensure correctness and consistency with the inputs of that phase. So because you can't really do a full end-to-end test of the product or system until the end of the development, you don't want to wait until then to make sure you're on the right track. And so throughout every phase of the life cycle, you're going to do some verification steps to make sure that, as well as you can, that the work that's been done so far has been correct. And these verification activities have to be planned concurrent to development. So before you do your development, while you're planning the development, you also need to plan what verification steps you're going to do along the way. Common verification steps are inspection, which is essentially a formal review of a document. Test, you actually can test parts of the system along the way, parts of the product to do verification before the entire product is available. And analysis, such as a failure modes and effects analysis, for example, where you analyze what are the failure modes are of the product and try to minimize that. And then ultimately there's a step called validation, where you do test the overall product to make sure it's compliant with its requirements, and that is a form of overall verification. So verification, as I said, applies to all the different phases throughout the life cycle. This shows a few of the examples here. It applies to requirements, test planning, architecture design, hardware design, etc., all the way down the cycle of the safety life cycle. So just as an example, how do you verify the steps along the way? You could look at safety requirements. You would do an inspection of them to make sure they're right, get people's opinions. You fill out a checklist that's probably closely related to the inspection to make sure that the requirements are complete. You plan on how to test those requirements, and generally the act of when you're trying to figure out how to test a requirement will often reveal flaws in the requirement, such as the requirement was not written clear enough to test, or it's not specific enough. And so that's that test planning can be considered a form of verification for those requirements. And finally, traceability between the product safety requirements and perceived safety needs. Traceability is something that's required throughout the life cycle. You need to trace requirements backwards and forwards, essentially show what the root of those requirements are and what gets implemented and tested as a result of those requirements. And so in this case, when you're reviewing the requirements themselves, you would want to trace the requirements to the perceived safety needs. So in other words, these are the customer needs that have been identified by the customer or a marketing group, for example. And you want to make sure that the requirements will meet that. And so traceability can go forward and backwards, and it mainly accomplishes two things. It mainly ensures that you meet all the requirements, or that you consider all the requirements going forward, and also that looking backward, that you don't implement anything that's not required. So generally, the more requirements you implement, the more complex the design, the more likely a failure may occur or a fault may exist in the design. So in order to keep it simple, you want to make sure you aren't implementing things that aren't requested. So that's how you verify safety requirements. Another example we could just look at briefly would be software source code. That also can be verified by inspection, somebody reviewing the code. Unit test, software source code can be tested in its units or functions or its smallest pieces essentially. So before you integrate it together in a large system, you want to test each piece to make sure that it works properly. Okay, you can also do,
There we go.
getting a little bit of feedback here. Hold on one second.
It doesn't come much louder than this.
Okay. So the software source code, static analysis essentially is a way to look at the source code statically. It can be done by a review similar to the inspection, but also there's a lot of tools out there, such as PC-Lint, if you're familiar with that, and there's several others that will analyze the source code and find potential problems with the code. And so that's another form of verification. And finally, fault injection test is where you inject faults and you use that to test essentially the error paths of the software. Okay, so those were the parts of the development that are independent of life cycle. Now we'll talk a little bit about the life cycle itself. This is the development life cycle. So as I mentioned, the overall life cycle starts at an end-to-end evaluation of what are the hazards that we're facing, and what do we need this system for, and that's usually done by the user of the system as opposed to the developer of the system. At this point, this is the life cycle that the developer focuses on to develop the system, and it starts with safety requirements creation. And if you're developing a system in response to a specific customer, like a custom system, then they may give you the safety requirements that come out of their hazard analysis. If you're developing a system that's a standard product, for instance, then you have to create your own safety requirements, basically guessing or predicting or knowing the requirements that your customer are going to need, the safety functions they're going to need, and defining that. That's followed by a system design phase where you essentially take the requirements and you allocate them to hardware and software and figure out the overall architecture of the system. In parallel, safety validation planning is done. So safety validation testing is what you do at the end of the overall development life cycle to show that the safety requirements have been met. And you can start planning that, and you should start planning that very early on in the life cycle, as soon as you have the requirements. One of the reasons for that is to identify problems in the requirements before people start implementing them. And another reason for that is to make sure that your planning is targeted towards requirements. Sometimes test planning gets targeted towards design, your validation planning, and it really should target the requirements. You might actually miss some requirements that way. Then the system design leads into the hardware design and implementation and the software design and implementation. And then in parallel to that, the detailed test procedures are developed. And then finally, the hardware and software are integrated together. Operation and maintenance procedures, so like user manuals are created. Something called a safety manual is typically created for products that perform safety functions. And then ultimately, the validation testing is done to make sure that all the requirements are met in the final product. All right, so we're going to step through these and go into details on some. The first one is the safety requirements specification. So the first thing you have to define are what are the safety functions of the product. It can be simple for products that have a straightforward function. A product safety function might be to measure temperature or measure pressure. It might just be a part of an overall safety function, for example. It could be a little more difficult when you're developing like a programmable system, like a PLC, for example, which the safety functions aren't really known by the developer. It's more of the end user will program in the safety functions. So in that case, the safety functions are more general. What are the functions that the system can carry out? And then per safety function, you have to define a safety integrity level. So 61508 defines 4 safety integrity levels, SIL 1 through SIL 4. SIL 4 is the highest, SIL 1 is the lowest, and essentially that is related to how much risk reduction you're looking for in a safety system. So a safety system essentially will reduce the risk of a hazard. If a hazard has a chance of occurring, once every 100 years, and you install a safety system that 99% of the time will prevent that hazard from actually causing any harm, then you can reduce the risk of that, or the probability of a dangerous event to be much less than once every 100 years, maybe once every 1,000 or 10,000 years. And then the mode of operation is also defined in the safety requirements. Are there different modes that apply to that function? Does the product work differently, like during startup, for example, or is there a sequencing or a learning phase, etc.? The safety performance needs to be defined. So if there's a function that has to do something like detect a condition and shut down, you need to define how quickly it must do that. And then the process that's followed for the requirements, the first half of it is just the standard documentation process. You need to have a template for requirements. You need to review the requirements. You need to have a checklist for completeness. In addition, you need to use something called semi-formal methods, such as truth tables or state transition diagrams that must be used to express complex requirements. So this applies to SIL 3, and this process overall that we are talking about does apply to SIL 3, although many of the same concepts apply to the different SIL levels. One of the ways the main way that standard differentiates between these different safety integrity levels is most of the requirements in the standard are common to all of the levels. However, the level of rigor that you must implement to meet various requirements is more rigorous for the higher SIL levels than others. So semi-formal methods are an example of something that's generally required for SIL 3 and higher. And so the main purpose of semi-formal methods is to make the requirements more clear than if you were to document them in plain English, for example. And just as an example, we have a pretty simple block here called which just does a division. It takes two numbers, x1, x2, and divides, and the result is output into y1. And then there's an S flag, which I guess would report if there's an error of some kind. And so it would seem like it would be pretty easy to specify what this block would do just by saying it should divide x1 by x2. But if you create a truth table and start to consider what are the different possible values that could be entered into this block, you realize that there's invalid and valid cases. What do you do if the denominator of the block is 0? What do you do if the numerator is 0 and the denominator is 0? And so that's all that is shown in here, the specific performance of this function in those scenarios. So that's the main thing that the truth table or decision table helps you do. It essentially helps you document what all the possible combination of inputs are, and how the system will behave under each one. I mean, it makes you think about it more, and up front, when you can tell what exactly you want done. If you don't do that, what ends up happening is the developer either consciously or subconsciously will decide what needs to be done, and if the developer doesn't understand the application, they might not do the right thing. All right, so once the safety requirements are documented, then there's the system design phase begins. System design consists of creating a system context diagram, which shows how the system interacts with the things that are outside the system. So it essentially defines what's inside the system, what's outside the system, and what are the interfaces. You decompose the system into subsystems or components, so you break the system down into smaller parts that can be easier understood and analyzed and implemented. And then you develop a safety strategy during the system design. And so design for independence is part of that safety strategy. As you break down break down the design into different systems, into different subsystems and components, if you can show certain components are independent from the others, meaning that they cannot influence the others. In other words, if they fail, they cannot cause the others to fail. You can then break your system into safety critical parts and interference free parts. And essentially, the interference-free parts do not have to follow all of the requirements of 61508 in your development. And so you could potentially reduce the overall amount of development work and overhead that's introduced by the standard by coming up with a strategy for showing independence between components. Hardware diagnostics are planned at this point. Software self-tests are planned, so the software generally will have some tests to test the hardware which are diagnostics, and it will also have tests to test itself to make sure it's running properly. You'll design a data integrity strategy at this point, which is what's the strategy for making sure that if data is either the data cannot be corrupted, or if it is corrupted, that's detected. Integration tests are planned at this point. So once you have decomposed your system into subsystems and components, you want to come up with a plan on how those components, once they're developed independently, how you bring them all together and make sure they work together. Do you do it all at once? If there's a lot of components, you probably have to break it down and test groups of components together and kind of build up to a whole system. And so that needs to be planned at this point. And then finally, there needs to be a review of the system design done at this point. All right, so the next step after the system design is to do what we call a failure modes and effects analysis at the system level. And so what you're essentially doing is looking at the individual components that have been documented in the system design and trying to figure out how they can fail and trying to make sure that you have ways to detect that failure built into your design. 61508 has various requirements related to fault detection. There's something called safe failure fraction that's required, which is essentially a ratio of all the failures that can occur to the product. A certain percentage of them must be safe failures, and I'll get into the definition of that in a little bit. There's also requirements for a probability of failure on demand. So what is the overall probability that the product's going to fail when it's needed the most? In other words, when the safety demand occurs, when it's needed to perform its function, when the gas level is high or the temperature is high or when an accident's about to happen and when these systems are relied on. So these things will need to be met. These requirements will need to be met, and it's important that during the system design phase, you consider making sure that you have mechanisms in place to meet them. So that way, once you actually get through implementation and are able to determine if you've met these or not, you should be pretty close, and you shouldn't have to do a lot of rework. So what you're essentially doing in the FMEA is breaking up the system into components, and then doing this sort of analysis for each component. So this analysis for a process sensor, what are the ways it can fail? It can have an inaccurate output greater than 2%, which is something called the safety accuracy, or less than 2%. So generally, if it's less than 2%, it's considered not to have an effect on safety. Now, that could depend on the application, but that's a general guideline. If it's greater than 2%, so the sensor is off by 10% or 50% or what have you, it certainly could affect safety, and it could affect it in a dangerous manner. So if you have some sensor that's supposed to detect a condition and it's off by 50%, it might tell you that condition does not exist when in fact it really does. And so that's considered a dangerous failure. When the safety condition or the hazardous condition is not detected or not acted upon when it does exist due to a failure, that's called a dangerous failure. And so that analysis has to go through. So for the sensor, a list of failures were identified. One protective measure was identified, that the sensor output is expected to be within a particular valid voltage range, which is less than the actual range. So essentially you can have a check of that range, and if it's outside that range, you can flag that as an error and take appropriate action. And so you notice here many of these failures have no safety measures, but two of them have this outside of reasonable range diagnostic. And then for each diagnostic that you have, there's a level of effectiveness of that diagnostic, and that's roughly means how likely is it to detect the problem. So, so it can be high, medium, or low, and that roughly translates into a high effective diagnostic should detect 99% or more of all problems. Medium effectiveness is 90%, and low effectiveness is 60%. So what do you do with this analysis when you're done? Well, in this case, some diagnostics were identified, but many failure modes did not have any kind of safety measures or diagnostics in place. And so, as a guideline, you should try to get measures in place for all the failures that are identified in the FMEA, and they should be medium level of effectiveness on average. So you can have some that are high, some that are low, but on average you would need medium level of effectiveness. Now, this is not a hard and fast requirement because ultimately we're going to calculate some actual numbers to determine whether the product meets the requirements for the safe failure fraction and for the probability of failure on demand. So during this phase, it's just a guideline that if you can have medium effective diagnostics on all major faults or all significant faults, then you're really likely to be able to meet the requirements or be close to meet them at the end. But if you're not exactly there, if you're not sure at this point, you'll find out later on in the process. So it's not a hard requirement at this point. All right, and then once the requirements are done, you can work on the safety validation planning. The validation will ensure that the system, the end system, the integrated system, complies with the safety requirements. And in this plan, you're going to define how you're going to do that validation. And so the requirement is that all safety requirements must be validated either by test or analysis, and most must be validated by test. So you're going to create tests to verify that most of the safety functions are working. It is understood that there's some that can't be tested via a test, and therefore they can be validated through analysis. So in other words, somebody analyzing some parts of the system to determine if the requirement's been met. However, you do need to validate every single requirement. So if there is a requirement that can't be validated by either method, that requirement needs to change so that it can be validated. It might just need to be more specific, or maybe it's not a real requirement. All right, and then at this point you create a validation plan. And you include in that a validation strategy, like for example, you're doing automatic versus manual testing. What are your test objectives? So for each requirement, what are the tests going to test for, essentially? And what is the required test equipment, if you know it at this point? You want to try to plan for that early on. The detailed test procedures don't have to be developed at this early phase. All right, so the next phase is the hardware design phase. And hardware design we can look at a board level hardware design and chip level. So if you're designing an integrated circuit, that would be like a chip level design. If you're designing a board that essentially takes a bunch of integrated circuits and other components together, that's more of the board level design. And essentially, most board-level hardware design processes will meet the requirements of 61508 with 3 additions required. And this is because the standard doesn't get into too much about the hardware development process overall, except for these 3 areas. So it doesn't get into too much about how you do schematic capture, whether you do simulation or not, how you do board layout, how you do some of your hardware-specific testing. So most processes out there should be compliant or pretty close to compliant due to the fact that there's not a lot of requirements there. But the 3 areas that sometimes are issues are component derating, failure modes, effects, and diagnostic analysis, and the rigorous development process at for ASICs and programmable logic. So the component derating essentially says that for each component, you cannot operate that component at its maximum rating on average. You want to derate it. So as a guideline, it says you want to operate below, say, a 33% derating, so that the component should not operate more than, say, 67% of its full rating on average. So this will significantly increase the reliability and the life of the overall product, and that's the main reason for this requirement. The 67% is a guideline. It's not a hard and fast rule, and if you have good justification, you can use different values for different types of components. And there are other standards out there that provide more specific guidelines for that. Failure modes, effects, and diagnostic analysis is an expansion of the FMEA that we just talked about. It goes beyond just looking at what the failure modes are and what diagnostics you have in place by basically adding a quantitative side to it, where you can actually calculate now what the failure rates are in terms of types of failures. So what's your failure rate for dangerous failures, for safe failures, and also in terms of detection, what percentage of those failures will be detected by diagnostics. And so that information is required to meet the requirements for safe failure fraction and probability of failure on demand. And we'll talk about this process in more detail. And then the last is the rigorous development process for ASICs, ASICs being application-specific integrated circuits, and programmable logic, such as an FPGA, field programmable gate array, for example. If your design includes either of them, there is a much more rigorous development process for those basically chip-level designs, and we'll get into that as well in more detail. All right, so an FMEDA is a structured quantitative analysis of a system, and its goal is to predict failure rates, failure modes, and their effect on operation while taking into account the diagnostic functions. As I said, it's an expansion of the FMEA technique developed in the 1990s, and the main addition to it is a quantitative failure rate. And it adds diagnostics and diagnostic coverage columns, and it's essentially focused on random failures. So in other words, the FMEDA does not consider design errors. If you have an error in your design and a component is overstressed and it's running at a much higher current than it was designed for, or much higher environmental conditions, much higher temperature, etc., that's going to shorten the life and lead to failures. The FMEDA technique, though, is not focused on that. It's focused on assuming that the design is correct, the parts are operating within their correct ranges, and there's still an expected failure rate of components even when they're not overstressed and when they're used properly. And those are considered random failures because they occur at random times. It's during the useful life of the component, too. The components have an expected life where they'll hit a wear-out mechanism, and this is the random failures that might occur before that point. And so this FMEDA is then used to calculate the items that are required by the standard for each product, the quantitative items, which is specifically the safe failure fraction and probability of failure on demand. All right, so I talked about a dangerous and safe failure. Here's just a more specific definition. A dangerous failure is defined as a failure that results in a situation where the system will not respond to a demand from the process. So this could be a failure where the demand is not sensed. So the demand is essentially the hazard that you're concerned about. So if the hazard is gas concentration, that's a demand. The demand would be when the gas concentration gets above a level that is perceived to be dangerous. And so a dangerous failure is one where you either won't detect the hazard, you won't detect you're above that level, or it's one where you can detect it, but whatever action you're supposed to take, sounding an alarm, shutting down the system, or whatever, will not work. So if the failure will impact either of those aspects, that's considered a dangerous failure. A safe failure is one that causes the module to go into a defined fail-safe state without a demand. So in other words, if the fail-safe state is to shut down the system, turn all the outputs off, a safe failure is one that does that even though there's not a demand, there's not a high gas concentration, there's not a presence of a hazard. There's also a type of failure called a no-effect failure, which is not safe or dangerous. So it's a failure that essentially does not prevent the safety function from working, nor does it cause a false trip, if you will, like a safe failure. That's called a no-effect failure. And that used to be considered a safe failure in the first edition of 61508. But in the second edition, that's now no longer considered a safe failure. It's not considered a dangerous failure. It's just not counted in the calculations. All right, so the method for analyzing the failure rates of a part include looking at the failure rates of each component, which is called lambda, and then breaking that into a safe and a dangerous portion. As it says here, the safe used to include the no effect failures. Now it does not. So really, there's a third option here. You need to break up the failures into safe, dangerous, and no effect failures. You don't really need to calculate the no effect failures, but you only need to calculate the safe and the dangerous. But the total failure rates will consist of the addition of all three. And then the safe and dangerous failures are then further broken up into whether they're detected or not detected by diagnostics. And this is mostly important for the dangerous failures. And the reason for that is that dangerous failures that are detected by diagnostics are called dangerous detected, and they can be considered safe failures because essentially you take an action when you detect these failures to put the system into a safe state, whether that's shutting down or alerting somebody or whatever, you take that action. And so then you're left with the dangerous undetected, the ones that are dangerous, they cause the safety function to fail, but nobody is alerted, no action is taken. So this is the concept of an FMEDA is relatively simple. What you do, actually doing one becomes a lot more complex. But the concept, I could try to go over briefly here. Essentially, you need to identify all the components that are part of the safety function, that contribute to the safety function, and you list them. So in this case, I'm listing just 4 components in this example. And then for each component, you need to identify what are the failure modes of that component. So we can look at this resistor, and we know for whatever type of resistor this is that there's 4 failure modes. It can fail short, it could fail open, it could fail with a reduced resistance or an increased resistance. And so this information is gotten from studies of actual field failures, for example. And those studies also can indicate what is the distribution of failures. And that tells you that 60% of the failures are open circuit, 10% are short circuit, 15% each for the change in resistance. And so there's various sources for gathering this information. Exida over the years has analyzed many of these sources and kind of summarized them in a data book that we create that essentially lists all the different types of components that you can use to build a system, including mechanical components and electronic components. And it defines what their failure modes are, what their failure mode distributions are, and what their failure rates are. So that is something that is available from us, but there's also other data sources out there as well, which is essentially what we use. We basically collected the best of all that information and put it in one place. Okay, and then what you need to do is once you've identified the failure modes for each component, you need to identify what is the effect of that failure in this specific circuit. Is it going to cause a shutdown? Is it going to cause a loss of the safety function, or what have you? So the effect kind of describes specifically what it does in the circuit, and then the behavior can either then be safe, dangerous, or no effect. Fit is the failure rate of the component. So the resistor failure rate is 0.13 fits, which is a failure per billion hours. And that is broken up among these different failure modes. So since you know the distributions of each of the failure modes, you know what the failure rate of each failure mode is. So for example, the short circuit failure rate is 10% of 0.13, which is 0.013. And then you can based on whether the failures are safe or dangerous, you can classify them to be in these safe or dangerous columns. And then ultimately, you identify if there's any diagnostics that will detect this error, and if so, what is the diagnostic coverage that you'll get from them, which is based on the effectiveness of the diagnostics. So in this case, this diagnostic shows a 99% coverage for open circuit, so that's a highly effective diagnostic. And then this diagnostic readback shows 90% coverage, so that's medium level of effectiveness. And so ultimately, by categorizing these into safe and dangerous and figuring out these diagnostic coverage for each failure mode of a component, you'll get 3 failure rates: the safe failure rate, the dangerous detected failure rate, and the dangerous undetected failure rate. And then these add all up, and so you can see for this product down on this line under totals that the safe failure rate is 13.56 fits, dangerous detected is 10.58, and dangerous undetected is 1.4 1.48. And these don't add up to the total failure rate of the product because there are some no-effect failures. And then to calculate the safe failure fraction, it's essentially the safe failures, which is the safe and the dangerous detective, divided by the overall safe and dangerous failures. So it essentially would be 13.56 plus 10.58 divided by 13.56 plus 10.58 plus 1.48, which comes out to 94.2% in the case of this product. And so 94.2%, if it's a SIL 2 product, that will say you can use that. It's related to redundancy, or what they call hardware fault tolerance. You can use that for SIL 3 in a redundant system at 94.2%, and you can use it in a non-redundant system for SIL 2 with that safe failure fraction. So there's essentially tables in there in the standard that relate the safe failure fraction to the level of redundancy that you need. All right, now we'll talk briefly about the ASIC development process. This applies to both ASICs, application-specific integrated circuits, and to user programmable logic, such as field programmable gate arrays and PLDs, SIA PLDs. It does not apply to standard integrated circuits, such as a standard microprocessor that's developed for many different applications. So the ASIC development lifecycle essentially follows this, what we call a V model. Development proceeds down the left part of the V and then back up the other part. That's kind of the direction it goes. And the items on the right are essentially verification steps for the items on the left. So we talked about having system or product safety requirements early on, and these now map into ASIC safety requirements. You'll need to have safety requirements for your ASIC. And when we say ASIC here, we're talking about both ASICs and the programmable logic like FPGA. This applies to both. So you create your requirements, your safety requirements for that ASIC. You define its architecture. What are the components or modules that connect it? Modularity is important in this design. You do your more detailed design and behavioral modeling, which is needed for simulation. And then you do module level design. So you've broken down the overall design into modules. Once again, the purpose is to make modules that are small enough that they can be easily understood by the people that are implementing them and testing them, and therefore more likely to be correct. The synthesis placement routing step takes the module design and converts it into a gate level design. So the module design is done using a hardware description language such as VHDL or Verilog. And then the final coding is done after the synthesis placement and routing. Some changes might be needed. Then post-layout simulation. After the placement and routing has been done, you'll do some timing analysis to make sure that the timing of the circuit is acceptable. Module level testing will be done to show that the modules functionally work properly. Integration testing, you'll integrate the modules together, make sure that works, and then you'll verify the complete ASIC, and then ultimately validate the complete ASIC against its safety requirements. So the ASIC development lifecycle mirrors the overall lifecycle for an ASIC. So there's four main phases of this lifecycle. There's the design entry phase, the synthesis phase, placement routing, and layout generation. And chip production. We'll talk about these first three. I realize I'm running a little bit behind here. We only have about 5 minutes left in the time, but I will continue going after the time. I'll try to finish as much as I will complete the presentation. So if you are available to stay on a little longer, that would be great. If not, sorry I was not able to get it all in the time. All right, and so in the ASIC design entry phase, where you essentially create the ASIC design, as I mentioned, you're going to use a hardware description language such as VHDL or Verilog. So these are languages that look a little bit like a programming language that you would use for software, but you're using this to define your hardware. You use tools that are proven in use, and what this means is the standard recognizes that the tools that you have that you use to develop these products are very important and can contribute directly to failures. In other words, if the tool fails, the product may have a failure in it, just as if you made a design error. And so the way this part of the standard implements that, it says that all tools must be proven in use. So the theory being that proven in use means it's a tool you've used before on many previous projects successfully. So if you've used it on other projects and they've been successful and they've worked, that shows to some level that the tool works pretty well. And so that's really the only way to qualify tools for ASIC and FPGA development. You need to create a modular design, as we discussed. You need to perform functional testing. You need to perform functional testing at the module and top levels, which is done via simulation. You need to design for testability in the final part. So essentially, the final part needs to have a 99% hardware test coverage, meaning that 99% of all faults where a gate would get stuck high or stuck low need to be detected in the final part, so you can prove out the final part at the end once it's been manufactured. And so in order to meet such a high level, you obviously need to design that in up front. And then you need to do a code inspection or a walkthrough, just like you would do for software. This is needed for the VHDL and Verilog code. Notice the items in red here don't apply to FPGA. So these requirements in general apply to both ASICs and FPGAs, but the ASIC requirements are more rigorous, and so there are a few requirements that we'll point out on these slides that don't apply to the FPGAs. All right, the next phase is synthesis. It's the process where the design is transformed into an implementation of logic gates. The requirements is you must do simulation to check that the timing constraints are met once the synthesis has been done. You must do a comparison of the gate netlist generated by the synthesis to the reference model, which is the VHDL code. And so essentially there's tools that will do this type of checking for you. The tools, once again, the synthesis tools must be proven in use. Use tools that you're familiar with and know work. Implementation of test structures. In order to achieve that high coverage of test coverage in the final product, you essentially need to build in some logic into the device that allows you to run tests on the final device, and so those are called test structures. And then you need to estimate the test coverage at this phase to make sure that you're on track for the test coverage you need to meet. The next stage is the placement and routing and layout generation, where you transform the logical design into the physical design on the chip. This is also done using tools and automated, and the tools need to be proven in use. There's also something called a design rule check that verifies that none of the design rules of the chip manufacturer are violated, which could be like minimum distances or things like that, maximum fan-outs, various things like that. And then there's something called a layout versus schematic check, which is usually an automated tool that takes a look at the output of the placement routing and kind of compares it back to the input and checks that it matches up. Okay, so that's the development for an ASIC. Next we're going to talk about the software development lifecycle. And the software development lifecycle, kind of also like the ASIC, it kind of mirrors the overall lifecycle. There's a software safety requirement specification, software safety validation planning, software design, software validation, so it's very similar. And if the product is developed with the hardware and software developed tightly together by a single group, a lot of these phases are combined. In other words, the safety validation planning is done for both the hardware and the software at the same time, and the actual validation is done at the same time. However, if there's different groups or different companies developing the hardware versus the software, then this might get broken down into two independent pieces that are fully tested and validated themselves. All right, and so the software safety requirements specification is the first step, and this is essentially based on the overall safety requirements specification. Essentially, during the architecture design phase, you go through and analyze all of the safety requirements, figure out which ones apply to software, and potentially write some additional requirements on how that is going to get implemented in software. Other than that, the same process that applies to the overall requirements development. All right, the software design and development we'll jump into in more detail. That essentially breaks down into these 6 steps here. Software architecture, support tools and programming language, detailed design and development, code implementation, software module testing, and software integration testing. We'll talk about some of these in more detail. The software architecture, the main goal here is just like we did for the system architecture. You decompose the system into different components and show how they interact together. And the other thing is you determine your safety strategy for software during this phase. So the software architecture must contain fault avoidance measures. These are measures to avoid or reduce the amount of faults that get into the design to begin with. And then fault tolerance measures are, assuming that some faults get through, that you can tolerate them in the end product. So the fault avoidance measures include the design methodology you use, the tools you use to do your design and development, and your notation that you use. And the tolerance measures includes methods for detecting errors and methods for recovering from errors and design features for maintaining safety integrity of data. All right, so the design methodology. For SIL 3, it's required that you use semi-formal methods similar to what we discussed for the requirements. It's essentially a more stringent way to define your design. Semi-formal methods are essentially defined as using a limited syntax language or notation to describe the design. So rather than just using free-form English to describe it, you're using something with a more definite meaning associated with it, such as a data flow diagram, a state transition diagram, class diagrams, sequence diagrams. So it's mostly graphical diagrams, but it could be a language too, some sort of some limited language that you use to describe your design, a structured language, for example. And then the design notation is important, and you need to have a non-ambiguous design notation. So in other words, if you're documenting your design with a bunch of rectangles and circles, you need to define exactly what they mean. They might mean different things for different people or different design methods. There is one well-known standard called UML, the Unified Modeling Language, that does define this notation very well, and that's recommended to use something like that. However, UML was developed for object-oriented design, and if you're not doing object-oriented design, it can be used, but it might not be optimal. Oftentimes, data flow diagrams are better, especially in safety applications. Methods for detecting errors consist of program flow control, which is essentially where you're detecting that your program sequence is correct and your critical parts of the program execute periodically at a high enough rate. So you might check that all the critical parts execute every second or something like that. So it's just something you need to make sure that the program flow control has not been compromised. And so this is a required diagnostic. And then data flow diagnostics, where you essentially analyze the flow of data into the system. How does data come into the system? How is it manipulated? And where is it output? And specifically, this is data that's part of your safety functions or your safety critical data. And so once you've identified that critical data path, you need to do something to verify that the calculations and manipulations are correct. So one example is reverse calculations. So if you do a calculation that's a multiplication, you could do something like a division, a different calculation to verify that it was correct. Another one is fixed floating point comparisons. You can repeat a calculation using both fixed point and floating point methods and make sure they come out close. Or another one is just reasonability checks. Normally, you might have a limited range where a calculation should result in, and if the result is outside that range, you know that some error has occurred. And then hardware diagnostics that are implemented in software, which are driven by the FMEDA. The strategy for that would be defined at this point. And then we also need to concern yourselves at this time with the safety integrity of data. And so if the data gets corrupted, how can you make sure that that's detected? You can use a CRC, which is a cyclic redundancy check. There's also something called a Fletcher checksum, which is a little bit easier to implement, but is only useful for smaller size blocks. So a CRC would, you'd calculate that on a block of data. That block of data changes, the CRC changes, and so therefore if that block of data gets corrupted, you'll find the CRC has changed and you can detect the corruption. Another concept is to use duplicate storage. So critical data, you can store 2 copies of it, and 1 copy you store inverted. All the bits are inverted. And by doing that, every time you access that data, you can do a comparison between the two, and that will show if either one has been corrupted. That's the strongest error detection technique, but it's the most costly in terms of memory and processor resources. Then there's something called temporal redundancy, which you can rely on if you're recalculating values periodically at a high rate. Then temporal redundancy will say that those values exist multiple times, and if one time they get corrupted, that'll be corrected in the next cycle. And so that limits the amount of checking required on things that are repeatedly recalculated. All right, once the system architecture is defined, typically you do something called a software HAZOP, or software hazard and operability analysis. And so this is a lot like the FMEA that we talked about for the system and for the hardware, and this is done on the software. Now the main difference is that for hardware, there's certain failure modes. You know a resistor can fail short or fail open, and it's pretty well known how they fail. But if somebody writes a routine in C or C++, everyone is unique for the most part. There's not standard components that people are using. The failures are well known. So you essentially have to analyze that code and try to figure out how it can fail. And a well-established technique for doing that is this software HAZOP. And it's essentially a systematic design examination to identify how the software can fail. Each component has attributes and process parameters, and deviations are examined by using guide words. So essentially it's like a structured brainstorming. You use these guide words to analyze the different parts of the software and figure out, brainstorm how it could fail. So it's not 100% reliable, but if you have a team of people working on it, 2, 3, 4, 5 people, you should be able to identify most of the failure modes, most of the likely failure modes of the software. And then you determine their possible causes and consequences. You specify possible safety measures. So once again, this is diagnostics you can put in place to detect the problems. And this allows you to have modules considered interference-free. So we talked about that earlier when I talked about independence. If you've done this type of failure analysis on software modules and have shown that a particular module cannot cause any of the safety functions to fail, then that module can be considered interference-free, and it does not have to have the same rigorous process followed in its development. And this will also identify diagnostics that you need on the software itself. So these are some of the examples of the guide words. So for example, there's no, more, less. So no means that no part of the function is achieved. So very simple, you look at what the function is of each component, and what if it just doesn't do that function? That's the most obvious one. Or more, if the function is supposed to calculate some value, what if it calculates a higher value, or it does things more times than it's supposed to be? So these are just guides, but you'll go through these 12 different words for each component, and these words will spark, okay, what are the possible ways the component can fail? And that's essentially how the HAZOP works. Just as an example, you might have something that's like a signal queue, and you look for each guide word, you say, okay, the guide word is no, so for this function, that would be like the signal is not queued. And what could cause it? Maybe the queue got disconnected. What are the consequences? That's not shown here, but that should be documented. Maybe that's a loss of safety function, or maybe it's just a loss of some non-safety function. And if it is a loss of a safety function, you want to make sure you have measures to detect it. And in this case, something is listed here called an online test of the message queue. And so you'll go through that for the different guide words. Note here that only 4 of the guide words are listed. It's quite common. There was 12 guide words we looked at, and you're not going to find a failure mode for every single one. Usually you'll find it for some, and others won't find any, and some will repeat themselves too. You'll find a failure mode that might apply to 3 or 4 guide words. All right, so the next phase is support tools and programming language. So this is where you pick your programming language and pick your tools. Just like when we talked about ASIC, tool failures in the area of software development can also cause direct failures in the process, and that needs to be in the product, and that needs to be considered. As far as the programming language, you need to have coding standards, which will essentially be used for all safety-related software. They should specify good programming practice, prescribe unsafe language features, undefined language features, unstructured designs. So essentially, things in the language that are not defined or that are likely to lead to trouble should be eliminated or banned, and by doing that, you hopefully can reduce the number of errors overall that are caused by the language. A good example of that might be like the go-to statement. It's preferred when you're doing program flow control that you do for loops or while loops or things like that. If you have a go-to statement, it might not be obvious to the coder where that is occurring, and therefore might be subject to error, especially during maintenance when a different person is to maintain the code. So you eliminate constructs like that, and that helps make the code to be more reliable. And then finally, specify procedures for source code documentation. What are the standards for documenting the source code? And on the tool area, whereas on the ASIC side, we just said all the tools have to be proven in use. On the software side, it goes a little further. It actually classifies the tools, and the main purpose of this is to show which tools actually can contribute to safety failures and which can't. So certain tools, like an editor, for example, are very unlikely to actually contribute to a failure in the product, and therefore you shouldn't have to use an editor that you have confidence from use in, for example. You should be able to switch editors with no problem. And so the way that's done is tools are classified to be T1 through T3. T1 generates no outputs which can directly or indirectly contribute to the executable code of the safety-related system. So essentially, it can't really lead to a failure. T2 supports test or verification of the design or executable code, where errors in the tool can fail to reveal defects, but they cannot directly create errors in the software. So if you have some tool you're using for testing, if it fails, it's not going to cause a problem. If the software was error-free, it's still error-free. However, if the software has a bug in it, you might not be able to detect it because your test tool has failed. So it's not as critical as a tool that can actually introduce a failure, but it still is a critical tool. And then finally, a T3 tool is a tool that generates outputs which can directly or indirectly contribute to the executable code. So the classic example of a T3 would be the compiler. If it generates assembly code different to what you designed it, it will not work as designed, and therefore that could clearly cause a failure of the safety function, for example. And so once you've done this, the T1 tools no longer have to be looked at. The T2 and T3 tools have to be qualified. The T3 tools must be shown that they operate correctly according to their spec, for example. And you can use the proven in use or confidence from use like we did on the ASIC tools, but you can also do testing. So if you're using a newer tool, you can do some testing on it to show that it's working correctly, or possibly even if the vendor is willing to share that information, the testing that they did, use that as evidence. For both T2 and T3 tools, you have to do a failure analysis. And so this is essentially similar to the HAZOP that we just talked about that you do in your own software. You need to do this on your T3 and T2 tools as well. And the main difference is you don't know necessarily the design of those tools, so you're doing this at the functional level. You say, what are the functions of the tool? And then you use those guide words that we looked at to try to figure out, well, how could this tool fail? What could it do? And then once you identify the failures of the tool, you need to have some mechanism in the process to possibly or make it likely to detect some of those failures. So some of these things are things that are in the process already. For example, if you have a compiler that generates bad assembler code, the assembler will not be able to create the machine code, and it will flag an error. So some things are detected already by the standard development cycle that you have in place. Others might not be, and you might have to add some additional checks into your process to look for certain problems. All right, so this is just an example of a tool classification. You would go in and list all the tools that you have that you're using for software development, what are all the versions, and then what's the criticality, like T1, T2, and T3. And then the tool's suitability is essentially what you have to do to qualify that tool. So tool criticality of T1, there's no qualification required, as we said. For T3, you might use confidence from use and a software HAZOP. So you would qualify it by saying you're using a tool that you've used before on many projects, and you'll do a software HAZOP to identify the failures. And T2 would just require the software HAZOP. It wouldn't require the confidence from use or testing. All right, detailed design and development is essentially where you take the software architecture and now you continue breaking down the software into further refinement into basically software modules, your lowest level modules or functions. You want to use modular approach, make sure the modules are small enough to be easily understood, easily tested, and the design of the modules must be documented, and you document software integration tests at this point. There is, for the modular approach, as I said, the size is very important because you want to make sure it's small enough to be easily understood. The source code standard should have a requirement related to the size. So it could be a size limit in terms of lines of code, like say 100 lines of code, 4 screens, or maybe complexity, cyclomatic complexity, less than 10. That's related to like the number of branches in the code. You decide the limit, but you want to put a limit in place that everybody has to follow. One entry point and one exit point in subroutines and functions. Variables encapsulate at the lowest possible scope. Avoid the use of global variables. So this essentially means if you have a variable in a function, all manipulations to that variable you want to take place in that function. So if a different person is reviewing that function later on, or changing it or maintaining it, they want to be able to see what can happen to that variable. If it's a global variable, it's quite possible it's changed somewhere else that person does not realize at all. So by making them, declaring them at the lowest scope possible, that means that only that file or function can access that variable, and that should be the goal. Modules communicate with each other through their interfaces, which are fully defined, and you don't use global variables. All right, code implementation now is when you take that detailed design and you convert it to code. You need to follow the source code standard. You need to review the code, have an in-person review all the code that's safety related, and you need to run static analysis on the code, which is essentially those tools like PC-lint that I mentioned earlier that will find potential problems in the code. And then you need to module test the code. So it's essentially testing each module, your essentially lowest level software unit, testing it by itself before you integrate it in with the whole system. And the theory is the modules are simple enough, you should be able to get significant test coverage, test them better than the whole system, and then when you start integrating them together, it'll make for a more reliable system. The module testing has a couple of requirements in what you must do for the module testing for completeness sake. You must define something called input equivalence classes, boundary value analysis, and structured testing are the 3 things. So input equivalence classes is a method basically used to come up with a small subset of possible inputs with the highest possibility of finding errors. So if you have several inputs into a function, those inputs might have hundreds or thousands or infinite possible values that could be passed into it. And ideally, you'd want to test every possible value and make sure that the function works properly with that. But obviously, that would not be practical. So if you're only going to test a limited set, this input equivalence class concept and boundary value help you come up with a good set of values to test. And so input equivalence classes says essentially that you divide up the input into different ranges where the function might be reasonably expected to behave differently. So just as a general example, if you had an input value that was supposed to be between 0 and 100, you could break that up into 3 equivalence classes, less than 0, between 0 and 100, and greater than 100. And you would test at least one value from each of those classes. So that would give you 3 test cases. And then when you consider the boundary value analysis requirement, what that says is you test the boundary values also, which would be the boundaries between the classes. So that would add 0 and 100 as a test case. And it also says you test very large values and very small values. So you add 2 more test cases. So you end up with maybe 7 or 8 test cases from this analysis as opposed to hundreds or thousands. And theoretically, it should give you very good coverage of most of the failures in this function. And in terms of coverage, the other thing you have to look at is actually all the code in the function. The goal is that all of the code is tested, 100% of it. Although the standard doesn't specifically state a percentage, and 90% is a target that's been accepted. But I would think because during module testing you can use a debugger, you can set breakpoints, various things like that. Your goal should be to get to 100%. If for some reason you can't, then 90% is like a fallback target. This is just an example of the equivalence classes. So if you have a value that's supposed to be between 1 and 99 here, you have a valid and invalid equivalence classes. The valid is between 1 and 99. Invalid is greater than 99 or less than or equal to 0. And so you would make sure you have one value from each of these classes plus the boundary values. If it's a Boolean, it only has two possible values, true and false. You want to test them both. So that's the general concept of equivalence classes and boundary values. The last step in the process is software integration testing. And this is where you're integrating software modules together. And if you have a large number of modules, you probably don't want to integrate them all together at once. So you break them into subsets that you integrate together, and then you create a plan, an integration plan for how you're going to integrate all of them together eventually into the whole system. And integration testing is something that's normally somewhat informal. Has to be a little more formal if you're following this standard, in that you need to create test cases and document your test results for the integration testing as well. Okay, I want to thank you for attending, and thanks for those of you that hung on. I know I went a little bit longer. It was difficult for me to. There's a lot of content here, so it was difficult for me to get it into an hour. I thought I was close, but apparently I still wasn't close enough. But hopefully you found value in the extra time. And this content will be made available on our website, and you'll be sent a link to it if you signed up for this class, and so you can review it at a later time. If you have any questions, I see some of the questions have already gone up. There's this Q&A menu. You can type in a question now, and I can answer. I also have my email address there. If you think of something afterwards or you have a follow-up question. So let me see what question I have now. Thank you. Okay, it's not a question, but Greg says thank you, and you're welcome, Greg. Thank you for. It's good, always good to get feedback that somebody hopefully got something out of the course, and it sounds like you did. So thank you. All right, I'll just wait on for another minute or two and see if there's any more questions. And other than that, thanks a lot, and enjoy the rest of your day.